Hello, in this video, I'll be working through Unit 1 homework problems 9 through 26. Number 9, we want the limit as x approaches 5 from the left-hand side of 2/5 x squared plus 2x. 2/5 x squared plus 2x is continuous at 5, so we're going to be able to evaluate this limit using substitution. We simply substitute 5 in for x, so we get 2/5 and then 5 squared is 25, plus 2 times 5, and that simplifies to 10 plus 10, or 20. Number 10, the limit as x approaches e of the natural log of x over 2x. This function is continuous when x is e. We're going to start with substitution. We'll substitute e in for x. We get the natural log of e over 2 times e. The natural log of e is 1. So you get 1 over 2e. Number 11, the limit as alpha approaches 5 pi over 3 of tan alpha over alpha squared. Again, we'll try substitution. So tangent of 5 pi over 3 over 5 pi over 3 squared. 5 pi over 3 is quadrant 4, so tangent is negative. Our reference angle is pi over 3. The tangent of pi over 3 is the sine of pi over 3 over the cosine of pi over 3. So sine pi over 3 is root 3 over 2. Cosine pi over 3 is 1/2. So that simplifies to just root 3. Over 5 pi over 3 squared. So 25 pi squared over 9. And the over 9, that part's going to flip up to the top. So we have negative 9 root 3 over 25 pi squared. Number 12, limit as x approaches negative 2 of x squared minus x minus 6 over 2x plus 4. Now when we try substitution here, negative 2 squared is 4 minus negative 2 minus 6. So we get 6 minus 6 is 0 over, and then 2 times negative 2 is negative 4 plus 4. We get 0 over 0. 0 over 0 is indeterminate. We don't know what that's equal to. So we have to try a different approach. Substitution is not going to work here. And if we think about this problem graphically, the reason substitution is not going to work is because this function, this rational function, is not defined when x is negative 2. So let's try using an algebraic approach instead. We can factor the numerator. So I'm going to reevaluate this limit. When I factor the numerator, I get x minus 3 times the quantity x plus 2 over, and when I factor the denominator, I get 2 times the quantity x plus 2. So there is a common factor. This is a removable discontinuity. And when I cancel out that common factor, now I'm just finding the limit as x approaches negative 2 of x minus 3 over 2. And this one is continuous when x is negative 2, so substitution will work here. Negative 2 minus 3 is negative 5 over 2, and that will be my limit. Number 13, the limit as theta approaches pi of sine squared theta plus 2 cosine theta. Let's try a substitution first. So we have sine squared pi plus 2 cosine pi. And we can simplify that. The sine of pi is 0. 0 squared is 0. Plus 2 times the cosine of pi is negative 1. So our limit is equal to negative 2. Number 14, limit as x approaches 3 of x plus 5 over x squared minus 9. If we try substitution, we get 3 plus 5, or 8, over 9 minus 9. So we get 8 over 0. 8 over 0 approaches infinity, or we can say that the limit does not exist. 15, limit as x approaches 3/2 of 8x cubed minus 27 over 2x minus 3. If we try substitution, we get 8 times 3 cubed, 3 times 3 times 3, 27, over 2 cubed. And in the denominator, we have 2 times 3 over 2, which is 3, minus 3. So this one gives us 0 over 0, which is an indeterminate form. Substitution does not help us evaluate this limit. So we want to simplify our expression algebraically and reevaluate. So we have the limit as x approaches 3 over 2 of, now on the top we have the difference of cubes. So the cube root of 8x cubed is 2x, and the cube root of 27 is 3. So first factor 2x minus 3. And then we're going to square the cube root of our first term, so 4x squared. Use the opposite sign. Multiply our two cube roots together, and then square our last term. Over our denominator, 2x minus 3. Now we have a common factor that we can remove, and we'll reevaluate our limit as x approaches 3 over 2 of 4x squared plus 6x plus 9. By removing that common factor, that removable discontinuity, what we're doing graphically is filling in that hole. There's a hole in the graph at 3 halves, when x is 3 halves. And by removing that and evaluating this simpler expression, we have filled in that hole, making the graph continuous at that point so we can use substitution to find the limit. And when we substitute in 3 over 2, we get 4 times 9 over 4 plus 6 times 3 over 2 plus 9, which is 9 plus 9 plus 9, or 27. So our limit is equal to 27. Number 16, we want the limit as x approaches negative 2 of the square root of 2x plus 5 minus 1 over the quantity x plus 2. We're going to try substitution to start. So that is going to give us the square root of negative 4 plus 5, or the square root of 1, minus 1, so 0 in the numerator, and then negative 2 plus 2, 0 in the denominator. 0 over 0 is an indeterminate form that does not tell us anything about the limit, whether it exists or whether it doesn't exist. So we have to try a different approach. We're going to simplify this expression algebraically and then reevaluate our limit. So to do that, we are going to multiply the numerator and denominator by the conjugate of the numerator. So I'm going to multiply by the square root of 2x plus 5 plus 1 over the square root of 2x plus 5 plus 1. And when I do that, I have the limit as x approaches 2 of 2x plus 5 minus 1, that's my numerator. And then in the denominator, I'm not going to multiply this out because I'm hoping something will cancel. So I'm going to leave this as the factored expression on the bottom. And when we simplify the numerator, 2x plus 5 minus 1 becomes 2x plus 4. (2x plus 4), which I could write as 2 times the quantity x plus 2 over my denominator, x plus 2 times the square root 2x plus 5 plus 1. Now I do have a removable discontinuity here. The x plus 2 in the numerator cancels with the x plus 2 in the denominator. So really we're finding the limit now as x approaches negative 2 of 2 over square root 2x plus 5 plus 1. And using substitution, this gives us 2 over the square root of 1 plus 1. So we get 2 over 2 or 1. Our limit is equal to 1. Number 17, find the limit as x approaches 1 of 1 minus the square root 2x squared minus 1 over the quantity x minus 1. If we try substitution, we get 1 minus the square root of 1 over 1 minus 1. So we end up with 0 over 0. And again, 0 over 0 is indeterminate, so we don't know anything about that limit. We're going to simplify this algebraically and then reevaluate. So we want the limit as x approaches 1, and we are going to multiply top and bottom by the conjugate of the numerator. So we'll multiply by 1 plus the square root of 2x squared minus 1 over 1 plus the square root of 2x squared minus 1. So that's going to equal the limit as x approaches 1 of 1 minus the quantity 2x squared minus 1 over x minus 1 times 1 plus the square root 2x squared minus 1, which simplifies to, so we have 1 minus 2x squared plus 1, or 2 minus 2x squared. 2 minus 2x squared. 2 minus 2x squared, we can factor out a 2 and we'll get 2 times 1 minus x squared. So this is just kind of side work at the moment. 1 minus x squared is the difference of squares. So that's 1 plus x times 1 minus x. Okay, so I'm trying to simplify. My ultimate goal here is to be able to cancel out this x minus 1 in the denominator. That's what's causing this removable discontinuity when I try to substitute in a 1. So we have limit as x approaches 1. And when I simplify and refactor the numerator, I get 2 times 1 plus x times 1 minus x over x minus 1 times 1 plus the square root of 2x squared minus 1. And I can, in fact, now cancel out the removable discontinuity. If I factor negative 1 from 1 minus x, I get negative x minus 1, and then those two cancel out. So now I have the limit as x approaches 1 of negative 2 times 1 plus x over 1 plus the square root of 2x squared minus 1. And substitution here gives me negative 2 times 2. I'm substituting a 1 in for the x over 1 plus the square root of 1. So negative 4 over 2 equals negative 2. My limit is equal to negative 2. Number 18, the limit as x approaches 0. Now we have a complex fraction here, so I'm going to start by simplifying my fraction. And the quickest way to do that is to find the least common denominator, multiply the numerator and denominator of the outer fraction by that LCD. So in this case, that lowest common denominator would be x times x plus 2. So I'm going to multiply top and bottom by that. So 1 over x plus 2 plus 1 over x over x, and I'm multiplying by x times x plus 2. Okay, now in the numerator, when I distribute like so, the x plus 2's cancel out, I'm left with x. And when I distribute that here, the x's cancel out, I'm left with x plus 2. And on the bottom, we have x times x plus 2. Okay, so I still have to take the limit, and this is a good opportunity for me to say, don't drop your limits here, because we still have not found the limit yet. We're taking the limit of this. Okay, so that is going to equal the limit as x approaches 0 of, now we can simplify, x plus 2 is 2x plus 2. And in the denominator, there's no need to multiply that out. You can. I'm just going to leave it factored. And now try substitution. So substitution gives me 0 plus 2 in the numerator, or just 2 in the numerator. And it gives me 0 times 2, or 0 in the denominator. When we have a non-zero finite number in the numerator and we're dividing it by 0, that is going to approach plus or minus infinity, in this case positive infinity, since our numerator is positive. So this limit does not exist. Number 19, we want the limit as x approaches 2 from the right-hand side. Substitution is going to give us 0 over 0. So we're going to simplify this algebraically by factoring both the numerator and denominator. So limit as x approaches 2 from the right of. When we factor the top, we have 3x and x. Then it's either 1 and 2 or 2 and 1. We want to get 7 in the middle, so we need to multiply the 2 by the 3, like so. It's positive, positive. And on the bottom, we have the difference of squares. So that's x plus 2 times x minus 2. And we can see that we do have a removable discontinuity. We can cancel out the common factor there and reevaluate our limit. So now we want the limit as x approaches 2 from the right-hand side of 3x plus 1 over x minus 2. Substitution gives us, so in the numerator, when we substitute in the 2 for x, we get 7. In the denominator, we get 0. Now 7 over 0 is going to approach infinity or negative infinity. Since x is approaching 2 from the right-hand side, the denominator is actually a little bit bigger than 0. So the numerator is positive, the denominator is positive, this approaches infinity, or we can simply say the limit does not exist. Number 20, find the limit as x approaches 3 from the right-hand side. Let's try substitution. So substituting 3 in for x in the numerator is going to give us 6 plus 5, or 11, over, and then 3 minus 3 in the denominator is going to give us 0. But since we're approaching 3 from the right-hand side, the denominator, really we should put in a number just a teeny tiny bit bigger than 3. So a number bigger than 3 minus 3 is going to be a positive number. So it's approaching 0, but from the positive side. So this is going to approach infinity since both the numerator and denominator are positive, or we can say the limit does not exist. 21, same problem, but now we're going to approach 3 from the left-hand side. So substitution gives us 11 over 0, but the denominator, we're actually approaching 3 from the left, meaning a number a little bit less than 3. So if you take a number a little bit less than 3 and you subtract 3, you're going to be left with a negative value. So 0, I'm just using this notation to indicate that we're approaching 0 from the left-hand side, so it's going to be a negative number. That means our numerator is positive, our denominator is negative, so we're approaching negative infinity, or we can simply say the limit does not exist. Number 22, we want the limit as x approaches 0 of sine of 3x over x. So I would begin by multiplying by 3 over 3 and then regrouping like so. So this is going to equal, we can bring the constant out, 3 times the limit as x approaches 0 of sine of 3x over 3x. And that limit is equal to 1, so we have 3 times 1 equals 3. 23, the limit as x approaches 0, x plus sine 2x all over x. So we'll start by splitting this into two limits. Limit as x approaches 0, Well, first let's start by just splitting up the fraction. So we have x over x plus sine 2x over x, like so. Now that's the limit as x approaches 0 of x over x, or 1, plus the limit as x approaches 0, sine 2x over x. So for the second limit here, I'm going to multiply by 2 over 2, and this 2 we can bring outside of our limit. So this is equal to, the limit as x approaches 0 of 1 is 1, plus 2 times the limit as x approaches 0 of sine 2x over 2x, which is 1. So our limit here is also 3. 24, the limit as x approaches 0, sine of 5x over sine of 6x. So I'm going to write this as sine of 5x times 1 over sine 6x. So we can kind of see what we're missing from our special trig limit. So for this first one, I would like it to be over 5x. And since I'm dividing by 5x, then to compensate, I have to multiply by 5x. And this is, of course, assuming that x is not equal to 0. But again, we're letting x approach 0. So we know x is not technically equal to 0. And then for this second part here, so that's good. For this second part over here, I want to multiply the top by 6x. And so to compensate, I have to divide by 6x. So now I have this limit here. And when I simplify, these x's cancel out. And the limit as x approaches 0, sine of 5x over 5x is 1. Limit as x approaches 0, 6x over sine of 6x is 1. So altogether, this limit is 1 times 1 times 5 over 6, or just 5 over 6. Number 25, we're given the fact that the limit of f as x approaches 4 is equal to -7, and the limit of g as x approaches 4 is equal to 2. And we are asked to find the limit as x approaches 4 of f plus 2. So we're going to split this up. This is going to be the limit as x approaches 4 of f of x plus the limit as x approaches 4 of 2. And we're given the limit of f as x approaches 4 is -7, so -7 plus the limit of 2 as x approaches 4 is just 2. So that answer is -5. Part B, the limit of 3 times f minus g as x approaches 4. So this is going to be 3 times the limit of f of x as x approaches 4 minus the limit of g of x as x approaches 4. So it'll be 3 times -7 minus 2, or -21 minus 2 is -23. Part C, the limit as x approaches 4 of f of x squared. So that's just going to be the limit as x approaches 4 of f of x. We can find that limit and then square that limit. So it'll be -7 squared, which gives us 49. Part D, the limit as x approaches 4 of g over f minus 1. So this will be the limit as x approaches 4 of g of x divided by the limit as x approaches 4 of f of x minus 1. The limit of g as x approaches 4 is 2 over, and then we can break this down as well into the limit as x approaches 4 of f of x minus the limit as x approaches 4 of 1. So that gives 2 over negative 7 minus 1. 2 over negative 8, or negative 1/4. Part E, the limit as x approaches 4 of 5 times f over g, we can write as 5 times the limit as x approaches 4 of f of x over limit as x approaches 4 of g of x. So that's 5 times negative 7 over 2, or negative 35 over 2. And part F, the limit as x approaches 4 of the square root of 8 times g of x. Well, we can write that. We can think of the square root of 8 times g of x as the square root of 8 times the square root of g of x. So we can bring out the constant, square root of 8, times the limit as x approaches 4 of the square root of g of x. And we can think of that as square root of 8 times the square root of the limit as x approaches 4 of g of x. So here is an example where we have the limit of a function is equal to, I guess you could say, the function of the limit. They can sort of switch places. So we have square root of 8 times the square root of 2, or square root of 16, which is 4. Number 26. At what points C does the limit of f of x as x approaches c exist? So we have a piecewise function, and it's defined as 3 minus x when x is less than 2, x over 2 plus 1 when x is greater than 2. 3 minus x is continuous everywhere on its domain. So to find the limit as x approaches a specific value of 3 minus x, we just substitute the value in and compute the limit. So that limit is going to exist everywhere on its domain. And for this piecewise function, that's when x is less than 2. So the limit definitely exists when x is less than 2. Now for the second piece of this piecewise function, we have x over 2 plus 1. That is also continuous everywhere. If you think about the graph of that, it's a linear graph. Continuous everywhere on its domain, and for this piecewise function, that would be when x is greater than 2. So to find that limit, as long as it's continuous, to find the limit, you just use substitution. Substitute your value in for x and simplify. So the limit exists for all values less than 2 and for all values greater than 2. The only thing we haven't considered yet is, well, what about at 2? So to figure out if the limit exists at 2, we have to approach 2 from the left and then approach 2 from the right. So we're going to take the limit of f of x as x approaches 2 from the left-hand side, and then we'll also consider the limit of f of x as x approaches 2 from the right-hand side. From the left-hand side of 2, that means numbers that are less than 2. So we're working with this piece of our piecewise function. And to find that limit, we substitute 2 in. So 3 minus 2 equals 1. So the left-hand limit is equal to 1. Now for our right-hand limit, as we approach 2 from the right, we're talking about numbers that are slightly larger than 2. So we're in this second piece, this x over 2 plus 1. So we're going to take the limit using substitution. We get 2 over 2 plus 1, which is equal to 2. So the right-hand limit is equal to 2. The left-hand limit does not equal the right-hand limit, therefore the limit does not exist. Okay, so the limit of f of x as x approaches 2 from the left is not equal to the limit of f of x as x approaches 2 from the right. Therefore, the limit as x approaches 2 of f of x does not exist. The two-sided limit does not exist. Okay, so the question asked us for what point C does the limit exist? And we've determined that it exists for all values except when x is equal to 2. So we could use interval notation if we wanted to. We could say the set from negative infinity to 2, not including 2, union the set from 2 to infinity. Or we could use set notation and say C is an element of the real numbers such that C is not equal to 2. Part B, same instructions. At what point C does the limit of f as x approaches C exist? So we have another piecewise function here. It's defined a little bit differently. The function is equal to 1 minus x squared when x is not equal to negative 1, and the function is equal to 2 when x is equal to negative 1. Both of these pieces are continuous everywhere on their domains, so to find the limit, we simply need to use substitution. So really the only questionable point here is negative 1. When x is not equal to negative 1, to find the limit, we just substitute that value in for x, simplify, and we're going to get a real number. So it exists when x is not equal to negative 1. If our C value is negative 1, we have to be a little bit more careful. We have to find the limit by approaching that from the left and from the right. Because remember, when we're talking about the limit as we approach negative 1, we don't really care what's happening at negative 1. We want to know what's happening as we get really, really close to negative 1. So let's find the limit of f as x approaches negative 1 from the left-hand side, and then the limit as x approaches negative 1 from the right-hand side. So as we approach negative 1 from the left-hand side, remember, we're not at negative 1. We're really close to negative 1, a little bit smaller than negative 1. Negative 1.000000001, for example, would be kind of a good way to evaluate that numerically. We're just a little bit less than negative 1. So we are in this piece of our piecewise function. And to find that limit, we're simply going to use substitution. 1 minus negative 1 squared. 1 minus negative 1 squared is 0. Now let's find the limit as we approach negative 1 from the right-hand side. Well, as we approach negative 1 from the right-hand side, we're just a little bit bigger than negative 1. We're not equal to negative 1. We're a little bit bigger than negative 1. So again, we're in this piece of our piecewise function. And we're going to evaluate that limit using substitution. So 1 minus negative 1 squared equals 0. The left-hand limit and the right-hand limit as we approach negative 1 are equal to each other. Therefore, the limit does exist as we approach negative 1. So this time, the limit exists for all real numbers. So we'll say C is an element of the set of real numbers. Or if you want to use interval notation, we can say negative infinity to infinity.